the specific rate of change of exponential growth and decay, and it works on a very, very basic idea. This is a very simplified model, that growth and decay is proportional to the population. Kind of makes sense. So the more people you have, then the more people that'll be born, the more people that'll die, and vice versa. So in other words, we're saying the rate of change is directly proportional, which we know we can write as equals some constant times p. So this differential equation, we know the solution to it will be in this form. Now at this stage we can just quote that. Next year we will investigate differential equations in a lot more detail and how to solve them. But for now we can say, well, we know the solution to this type of equation will be this. P equals some constant times e to the power of kt. So P is the population of what we're investigating. A turns out to be initial population. Has to be when you think about it, because when t equals 0, we're going to get e to the power of 0, which is 1. So it must always turn out to be the initial amount. K is our growth, or if it was negative, it would be decay. Constant, t of course is time. Let me go and prove it. So at this stage, as I say, they won't ask you to find the solution, but they might ask you to show that a solution works, which we can do at this stage, because that just involves a bit of differentiation. Now if the solution is p equals ae to the kt, when I differentiate that, I'll get ka e to the kt, which is k times p. There we go, we've proven it's a solution. An example, the growth rate per hour, a population of bacteria, 10% of its population. Initially we have, how many zeros have I got there? We've got 1 million bits of bacteria. Imagine them, there they are, crawling all over your hand even as I speak. You can't see bacteria of course, but there they are. There's 1 million of them all around, growing at 10%. As I say, okay, show that this is indeed a solution. In this case, we haven't got k because they've told us the rate is 10%, so we've just made it 0.1 t. So as I just did before, all right, well, if you reckon that's the solution, I'll differentiate it, and yes, that is k, in this case 0.1, times the population. That works. Then it becomes a bit of a substitution question, really, because we now know the actual solution. So determine the population after 3.5 hours. Correct to 4 significant figures. The initial population is 1 million, so I can now adjust my equation a bit more. And all I've got to do is substitute in t, and we get our answer. So, wow, another 419,000 bits of bacteria are now crawling all over my hand. On an island, the population in 1960 was 1,732, but in 1970 it was 1,260. Let's find the annual, well, they've called it a growth rate. We know it's going to turn out to be a decay rate, to the nearest percent. So p to t is equal to some constant times the population. This we know, we're assuming that anyway. So we know the solution will be in this form. We know initially there's 1,732, therefore I can refine my equation. We want to find k. The other piece of information is after 10 years, it's 1,260. We've got an exponential equation to solve. E to the power of 10k will be that. Log both sides, divide by 10. That's the exact value. But of course, for a question like this, yes, they've said to the nearest percent. We need to calculate that out. So that's 3%, well, negative 3%. So I could answer that by saying the growth rate is negative 3%. I suppose the other way I could have just said is the decay rate is 3%. Either way, it answers the question. Well, how long, how many years will the population be halved? Yeah, well, half of that population is 866. Again, we have an exponential equation to solve. T equals 1 on k, the log of a half, which is our standard, well, half-life formula. 21.786. So the question is, in how many years? Well, 22 years. Had that answer been 21.2, I would still say 22 years. Now, this is not one where I'm going to round down because they're saying in how many years. If it was 21.2 and I said 21 years, well, no, it hasn't halved in 21 years. It hasn't halved yet. So the answer would still be 22. That's why I think it's always safe with these sort of ones is, sure, write down the decimal answer to a few decimal places, then draw a conclusion from it. So if you do draw the wrong conclusion, it's probably still going to be okay because they can see, well, you did calculate the right one out. 16b shall do us.